and we know in science when you've got a good idea, sometimes you have to exaggerate your position a little bit so you get more attention. Wallflowers don't get much attention. This is the last lecture on the real business cycle model approach to looking at macro fluctuations. And the last 3 lectures will deal with the new Keynesian approach. So the idea is to give you a foundation for your understanding of macroeconomic fluctuations from 2 perspectives. And this one we're giving you right now is one that is completely non-monetary in nature. So there's no banking sector, there's no money, there's no price illusion or wage rigidity, nominal wage rigidity. There's no unit of payment. And the idea was to as Prescott and Kinland in their initiative in the 1980s to ask the question, which was a well-formulated research question, was whether you could generate fluctuations alone, in a world where money is more or less irrelevant. Money is neutral. And the answer is yes, but we'll see at the end of this lecture that there are some limitations, and that's why the real business cycle paradigm is probably more readily seen as a stepping stone for more advanced ways of looking at the macroeconomy. And I do urge you to think very hard about this as a building block, as a tool in the toolkit of macroeconomics. Okay, so let me summarize what we're going to do today. We're going to obviously review last time quickly. I'm going to finish the derivation of the real business cycle model, the stochastic growth model. It's called that because it's a stochastic discrete time variant of the model you dealt with last year, the Ramsey model. This being a market equivalent, so the agents are optimizing given the prices they face, the expected future prices they face, and given their wealth. And there's a single agent. So it's a very simple, rarefied view of the world to give you some insight into some of these key things that drive agents to behave in certain ways, to substitute consumption from the past to the present to the future, or to save and invest more, work harder, etc. Okay, so we'll finish that. And again, this is a foundation for everything that you'll do in the future, so it's important to understand the principles. It's a lot about finding a set of equations and a set of unknowns that are equal to each other, so the model is determinate. At least it's on the face of it. But again, it's an expectational model, so it's going to also depend on, the agent's behavior will depend on expectations of future variables. So to understand the solution of that model, we have to solve it. And nonlinear models are not easy to solve. The lesson of this lecture and of this course is that the basis for understanding fairly complex models is to take an approximation of that model. And we're going to be taking a log linear approximation, which means we will look at the variables, the original variables like consumption of the representative agent, the labor supply of the representative agent, the capital stock of the representative agent, or the economy in general, and then think of the behavior of the logarithm of that variable as a fluctuation around its steady state value. And that turns out to be a linear system of equations. So if you understood what we did in the past 3 weeks, all the stochastic difference equation stuff, this is where it's going. We're going to actually use a model that's based on first principles, microeconomic foundations, and we're going to thrust it into an approximation mode that is actually susceptible to analysis. Okay, so that's a key step. One of the things you'll learn in this course is how to do a log linear approximation. And to do that, we'll go into detail. Andreas promised me a few minutes ago that he's going to do that with you in this section. It's really something for your life. Even if you're a microeconomist, you want to do econometrics, a log linear approximation of a nonlinear relationship is an extremely useful thing to know how to do. Okay? Having done that, we will convert the system that we characterize as an equilibrium into a set of linear equations and the logarithms of these variables as deviations from the steady state. And then we can actually use solution methods to figure out where the model goes when it's shocked. So when a single shock hits the model, we will draw the impulse response just as we did before with the baby toy model, the ASAD model. We'll be able to do this for a grown-up model and see how that works. And there are 2 ways to do this that I'm going to teach you in this course. One is called the eigenvector eigenvalue decomposition. So it'll make use of properties of the matrix that expresses the relationship of the current endogenous variables as a function of the lagged endogenous variables and shocks, okay? And the other one is kind of the cheapo way of doing it, which we call the method of undetermined coefficients, or MUC. Okay, so that's the way a lot of people sort of cut through the quick and get the quick understanding of what's going on. Because the system is linear, the proposal will be that the solution has to also be linear, a linear function of state variables, and therefore we just have to solve for those. We just have to solve for those undetermined coefficients. That's a fairly frequently used method in some microeconomic applications. When you're trying to solve for an equilibrium and you just know that it takes a certain form, then you're allowed to do this. Okay, so this is something that we actually do in real life. And knowing both of those, they're intimately related to each other, but the second one is kind of easy. And there's a paper on the reading list by John Y. Campbell, who's a professor at Harvard, who's actually wrote one of the first papers that actually made it very understandable what's going on. It was called Examining the Mechanism. So he was writing a critique of the real business cycle model in the 1990s, and he actually wrote it down in such a complete way that, you know, I still use this in my course because it's a really nice way to see through this veil of complexity and try to get an idea of what's going on. And he pushes this method of undetermined coefficients as well. Okay. Then I'll finish the lecture by talking about the critique of the RBC model. We don't use the RBC model as a sole way of thinking about the world. It's got its limitations. Prescott went out on a limb and said that it explains 90% of the variance of the US GDP, or 70%. These were obviously very extreme claims, but I think we know in science when you've got a good idea, sometimes you have to exaggerate your position a little bit so you get more attention. You know, wallflowers don't get much attention. So that's kind of the way I like to see this. But he got the attention, got a lot of criticism. If you go on the Moodle site, you'll see that I posted his paper where he goes alone. I think it was published in 1986. And Professor Summers, who was my employer at the time, actually was discussing that paper, and he made fun of it because he said, this can't be a characterization of the real economy because there are no prices, there's no money. How can that be a real economy? Okay, it's really aggressive, and Prescott was really taken aback, so much that he actually wrote a reply in the same issue. It was published by the Reserve Bank of Minneapolis of the Federal Reserve System. And it's a nice exchange. If you like that kind of stuff, you can see how academics, you know, sort of lock horns and fight. And it's actually a very non-technical discussion, but it's clear that Summers had some points that got under the skin of Prescott, and Prescott responded in kind. So it makes for lively debate. Unfortunately, we don't see much of that going on these days, but it comes and goes, right? So it's an interesting, and we'll come to those points at the very end of the lecture. Okay, so last time we formulated the stochastic growth model. I'll alternately call this the RBC model. We wrote down the problems. There are two problems of concern. One is the utility maximization problem of the household, which is a dynamic problem looking forward, hard to look at, hard to think about. And then we had a firm problem, which is just sort of the firms are the tools of the household. The firms just do what the households tell them, and there's no dynamic optimization. That's the way this model is set up. It's not the only way to set up these kind of models, but it's very easy for students to learn and get a grasp of what's going on. Okay, so we had those two problems. We got some first order conditions which characterize optimal behavior. We have a budget constraint and we have a transversality condition. And we also thought about the firm facing this sole shock in the model, which is this technology. So the firm is trying to maximize profits and the production function keeps shifting. And it does in a semi-systematic way. There's a random part and there's also a predictable part. So if there's a positive shock to the production function's productivity, TFP, then firms say, wait, you know, maybe it's a good idea for me to rev up my production, not just today, but also into the future, because there's money to be made. My capital and labor are productive for the next few periods. And conversely, if there's a negative shock, if productivity decreases exogenously, that it portends bad news for the future, and firms might want to rev down their production. So we'll get back to this. The interpretation of the technology shock is very controversial. Summers will also criticize this. He said, how can productivity go backwards? How can you have regress? Well, there's an easy answer. okay? But this total factor productivity is a measure of the value added you're able to produce with capital and labor. And if the stuff you are producing suddenly loses value in world markets, for example, or if the price of oil goes up and suddenly you're not as profitable as before, these are things that are not mapped in directly into the production function. Therefore, they look like productivity regress. Okay, but you can take any position you like in this. The idea of having a negative shock is certainly the source of a lot of debate. Okay, so this is, it's kind of fun to think about this. But it is the sole forcing model, variable in this model, which makes it really, for me, intellectually interesting to think about. You know, the model is so clean and understandable, then we can actually have a serious debate about the facts. It's not a matter of ideology. I mean, we've basically shut down the monetary sector for a reason. We want to see what we can do without it. Okay, and then you can judge from the way this course is going that that's not the answer is not affirmative. Okay, we characterize the decentralized market equilibrium. So firms are taking the price of capital, user cost of capital, this U variable we defined, and the wage is given. The workers also take these things as given. They're basically determined in a competitive market, and we know how that works. Okay, so there's no price manipulation in this model. It's basically it's just, again, a benchmark that we can criticize in the future. We characterize those decentralized market conditions. We substitute away for the prices in terms of their marginal products. And then the next step, which we'll pursue today, is to identify the model's steady state and then think about the fluctuations around that steady state. Okay, so think about Germany. Okay, this is German growth since 1971. You see there's quite a bit of fluctuations. These are percentage annualized rates of growth. Okay, so these are basically quarterly rates of growth. You see there's the Great Recession there in 2009, and you see that it was big, but there are other ones that are quite big too. I mean, the first oil shock, 1974, 75, and then we had the 1979 oil price shock, also associated with big drops in GDP. The consequences of the Bundesbank presumably raising interest rates in 1991, 92 caused the German economy after unification to cool down quite a bit. So you can see these are like recurring shocks, and you know we showed in the previous lecture that you can use a low-order difference equation to characterize that. Sort of autoregressive process of order 2. The same is true for the United States. Doesn't look exactly the same because the U.S. is a different economy, different things they're producing. And you also see that there's a trend in the data. Okay, so and these trends are not immutable and written in stone. So to me, this is a very interesting picture, which continues to baffle a lot of my colleagues, myself as well. If you just look at the United States, and this is the raw data. This is not logarithm in logarithmic form. It's just the data. You know, sort of billions of dollars. So 18,000 billion is 18 trillion. You know, million. So it's quite a bit of stuff there. This flow, but you can see that in the Great Recession something happened. And if you just extrapolate what we were doing before, using any sort of normal extrapolative log linear trend, you'd get something like the dotted line. So we've really seen a big change in the United States trend, something that we have to go back to growth theory to understand. What happened in the United States? Was it a drop in TFP because of maybe the shifting of the destruction of the financial and real estate sectors that resulted from the Great Recession, or the loss of competitiveness that was kind of in the making in the United States, the automobile sector, for example. But you also see that consumption dropped. Okay, so it's not like Americans just keep on consuming willy-nilly. It's actually American consumption looking forward, obviously anticipated that these times were not going to be great moving forward. And even despite all the hype of the Trump administration, we haven't recovered the trend yet. U.S. economy is growing faster, but still ain't growing at the rate that would be necessary to recover the trend. Okay, now compare that with the German economy. Okay, so this is the German economy in the subsequent years after the Great Recession. You see that there was a big drop, but the underlying trend in Germany didn't change much. Still, if you fit a log linear curve to that, you'd get a slight decrease after 2008, but nothing near what you have in the United States. The U.S. looks like a discrete drop in the level of GDP And this is not a measurement error. This is real stuff. This is lost welfare in the United States, lost goods and services. And you also see that German consumption doesn't change in its behavior at all. So it's really unchanged from its trend, which is an interesting fact as well, because economists are challenged to write down a theory that could account for that. And what we've done already is kind of in the position, if people have sort of reasonable expectations of the future, and I say rational expectations, they kind of understand what's going on. The German economy was sound before the Great Recession, and it's kind of still sound afterwards. Maybe in the future we'll have problems with cars and other things, but right now things look pretty good, and consumption seems to follow a trend that's consistent with that expectation. Okay, so now let's keep that in mind as we start thinking about a model that's able to maybe capture both of those things. First off, you're going to have to think about the trend in the United States changed. So we're not going to allow for changing trend in what we're doing, what follows, but keep that in mind. If we're absolutely sure there's a change in the trend, we'd need to think about that as well. Okay, so what is a general strategy for solving the model we just looked at? And I'm going to list those equations in a second, but first I'm going to give you a verbal summary. And it really makes sense to study these slides and go to the section tomorrow, because Andreas is going to spend the next 2 sections talking about this in detail. First, you've got to find out where the economy is going to stop fluctuating. If you take all the shocks away from this artificial laboratory we've developed, where does the economy settle down to? Okay, we already had a notion of that from the ASAD model. Where does the economy stop fluctuating if we take all the shocks away? That's called the steady state. And we're going to try to characterize that steady state with the model we have. We can write it down. You can write it down on paper. You don't have to do any computer stuff. And you can basically think of this as a way that can be guided by looking at data. We'll talk about that in a few minutes. We'll talk about how to calibrate the model, how to use observable data to discipline the choice of parameters. Because right now we just have a beta. We have an alpha. We have a nu. We have a g. Those are the parameters. It's a very low parameterized model. We still have to choose values for those things if we're going to try to simulate this model and match the German data or the United States data. Okay, so we'll use the so-called calibration approach in this course to motivate choice of parameters. There is no Wikipedia entry for alpha. You can't just go look it up. You have to use the data to discipline. The alpha in Germany is probably, if you take this model really seriously, is different from the model's best choice of alpha for the United States. Okay? Remember, alpha is the capital elasticity in the production function. Okay, so that would be, in a competitive model, that's going to be the capital share. Okay, so in the United States, it's a number like 0.35 or 0.4. In Germany, it's more like 0.45. Okay? Then we do the log linearization step. That's going to require a bit of algebra on your part. I really beg you, I'm getting on my knees to beg you to do this. Okay, if you really want to maximize your gain from being here and spending this time every Tuesday morning and watching my crazy videos, you need to do this. Okay, you need to practice this. So one of my colleagues from earlier, Harold Uhlig, he basically had a cookbook of ways of doing this, because there's, once you get the hang of it, it's quite easy to log linearize log nonlinear relationships. You're basically taking an approximation of something we have in our model as a theoretical implication, and we're making it saying, okay, well, suppose we just take very small changes. If the shocks are tiny, can we approximate that in a linear form? And that will enable us to do all the other magic with this model. Okay? And after that, we can actually try to solve the model and use the difference equation methods that we've done. So we'll look at impulse responses. And I'll take you through this. At the end of the hour, I'll actually present this RBC model when it's shocked once by a shock to productivity. Okay? And then after that, nothing happens. The model just goes back to its original starting position. And we'll see how that helps us understand the dynamics and try to match that with the economy's behavior. Okay? So let me go into detail now. Okay, I'm going to, again, the idea is to always, the Slutsky idea, shocks versus propagation. We're going to use our language that we used before. The control variable. Okay, what is the control variable? What can the consumer or what can the firm do given the capital stock it has, given the state of technology it observes. Those are the state variables. Those two are the state variables. The control variable is how I optimally respond to that. Okay, so remember the Ramsey model, that was not an accident that we presented it in that part of the course. It gives you the intuition that the Ramsey planner can adjust consumption freely at any point in time to do the right thing going forward. And that's exactly what our representative household is doing. Household is free to choose consumption in this model looking forward, given the capital stock it owns and given the state of technology today. Okay, so that gives this is a very important terminology in macro. Okay, because modern macro, dynamic optimization, control variables, and then you have state variables. State variables are things you cannot change. Capital stock today and its deviation from the steady state are given. It's the consequence of having accumulated investment in the previous period. Okay, so you didn't consume in the last period, you have more capital today. Think of that period as just nailing the stuff to the floor, building the factory, producing the computers that are now going to help us produce more output. Okay, you always have this consumption versus investment distinction. That's what makes the model so interesting, because we know that investment and consumption in the business cycle move together. So even if you believe in a Keynesian world, you need to account for that. It's very rare to have a business cycle where investment is rising and people are holding back on their consumption. It's usually because people want to do the right thing for themselves and for their families. They're also going to raise their consumption, albeit at a lower rate. Okay? In the RBC model, the control variable is the consumption of the representative household, and particularly, we're going to talk about the deviation of consumption from its steady state path. Okay, so we're going to have a special notation for that, et cetera, and that's given capital and technology. So exactly what I said before, I'm saying it again, and you should really remember that. So the idea is to use that control variable, and we also know that employment is chosen by the household optimally, but there's no intertemporal aspect of the household's labor supply decision except for the fact that if the household works hard today, it's going to have more stuff, it's going to be wealthier into the future. Okay, so the household's effects on labor supply on its other behavior is purely through increasing or decreasing wealth. Okay, so this is a simple starting model. You can get into much more complicated models, but understand these mechanisms. Okay, we want to be able to replicate the fact that labor supply in the German economy actually moves. Okay, it's not constant. It moves with the cycle. It's pro-cyclical. And labor supply in the United States is even more pro-cyclical than it is in Germany. And these are facts that we need to account for. So if we're going to try one of these representative agent models, we've got to get this right. Okay? So now I'm going to define an equilibrium, given what I did last time. We wrote down these first-order conditions. I'm going to write them down now, again. Defining an equilibrium as a set of sequences, okay, starting from T0, the agent starts in T0, looking forward, and these sequences have to be consistent with the following four conditions. We already did this one last time. That was the intra-temporal optimality condition for the household. The household supplies labor to the point where the marginal disutility of labor supplied today is equal to the marginal utility of the resources it gains by earning the wage. Okay, and I've substituted for the wage. That's in the numerator. The denominator is consumption because 1 divided by consumption is the marginal utility of resources. Okay, so this is a really intuitive, this is the most intuitive thing I've written down. This is the marginal disutility of working on the left-hand side is equal to the marginal utility of the wages earned on the right-hand side. Okay? Now that's a very nonlinear expression. If I take logs of that, you'll see it becomes linear in a very beautiful way. I don't have to play with this very much. This is an easy one. You take the logs of that, you got a log linear relationship already from the get-go. But the other ones aren't so cooperative. Okay? We also had the so-called Euler Equation, which kind of relates my marginal utility of consumption today with the marginal utility of my consumption tomorrow. It's like an intertemporal arbitrage condition. If I'm behaving optimally, then my marginal utility of consumption or resources given to me today has to stand in a fairly clear way to the marginal utility of consumption tomorrow. And that clear way has to do with the rate of return on saving, okay? We call that U, but it's a transform of U. You can see that it's basically accounting for depreciation in this case, okay? And at the same time, we've got consumption tomorrow, because consumption tomorrow, the inverse of that is the marginal utility of consuming tomorrow, okay? So if I do the right thing, if I'm optimizing, the marginal utility today has to be tightly linked to the expected marginal utility of resources I put into the production function tomorrow. And the beta stands there because I discount naturally in a deterministic way utility in the future. Okay, so this is called the Euler Equation. For those of you who take Max Brucha's course, this is one of the foundations of modern finance. Lucas showed that you can manipulate this equation to make it look like an expectation of the marginal rate of substitution with the gross rate of return on assets has to be equal to 1. Okay, so that's kind of the so-called Lucas asset pricing model is basically coming from this equation. So Euler equation, Euler equation, call it what you want, is a very important relationship. It is certainly not so simple to log linearize. Look at that baby. It looks pretty awful. You've got additives, and if you take logs of that, you're going to get, on the left-hand side, you're going to get a minus ln of c, but on the right-hand side, you got a log of an expectation, so you're going to have to do some approximating. Okay, we're going to approximate this thing, and then we're going to take expectations. We'll get to that in a second. That's why I keep saying the log linearization is something you really have to practice, like learning how to ride a bicycle. Once you do it, you'll never forget it, but you really have to do it. Okay? Here's another interesting relationship. This is the resource constraint. We called it a budget constraint before, but for the representative agent generalized to the economy, it's also a resource constraint. It says that the capital stock that's available tomorrow has to be equal to what we didn't depreciate in the previous period, plus what we produced in the previous period, minus what we consumed in the previous period. Okay? So that's just a simple extended version of the Goldsmith equation for investment and capital stock. Okay, and that thing is also kind of nasty in the sense if you want to log linearize that thing, you're going to take a logarithm on the left-hand side. That's easy. The logarithm on the right-hand side is a log of sums. It's not equal to the sum of the logs. Okay, that's a fact. So bear with me on that. And the final equation is the evolution of the only shock in the model, which is this technology business. Okay, so the position of the production function is shifting every period, being shocked by this epsilon. So if you take the logarithm of that, it's actually quite beautiful. Okay, you take the log of that and you get something that's actually log linear. Okay, and it's log linear around a deterministic state at which little g is growing at the rate of the z bar times a function of time is growing at a rate approximately equal to little g. Okay, so that's the rate of growth of the economy. All right, so we'll come back and do this in detail. So we have, in a sense, in any given period, we have 4 equations and we have 4 undetermined variables, given the expectations of the future. So that's the most important thing you should remember. Holding the expectations of the future constant, okay, we have 4 equations and 4 unknowns. So we can actually do something with this. Okay, but again, I told you we have to approximate this economy because this is already very complicated. Imagine what the Bundesbank is doing. I mean, if you take their sort of medium scale macroeconometric model based on several of these principles, it might be 100 times as big. So you obviously need a computer to do that, and you also have some very complicated relationships going on there. But understand this, and you're already on your way to understanding what they have to do. We're still going to have to approximate it. So we're taking a log linear approximation of this thing around a steady state. So we have to identify that steady state. What is the steady state? I told you, it's when the model is not shocked. Absent the shocks, what does the model do? If you look at the last equation, you see that z is the driving force of the model. And if I turn off the epsilon, if I let epsilon equal 0, okay, then e to the 0 is equal to 1. That's gone. All that's left is something that's growing every period. Okay, and that's this deterministic part. So that's going to anchor, just like in the Ramsey model, it's going to anchor the progress of our economy. So that's what we need to do. We need to think hard about that steady state. So that's what this slide is about, is trying to show you what the steady state looks like. It's the set of CT, LT, kt plus 1 and zt that have the following properties. Okay, first, everything that is growing at a common rate. Okay, if you remember the very beginning of the course, I talked about the Caldor facts. Remember certain things about the economy that kind of are constant and the other things are growing, and they're all kind of bound by these ratios. And one of them was was C divided by Y. Looks like a fairly constant thing, or the labor share. Okay, these are things that we want the model to be able to give back to us. So the model, this RBC model is kind of cooked to give those things back to us. First off, ZT will grow at the rate G. Okay, so every period in a steady state, ZT is equal to 1 plus G times ZT minus 1, absent the shocks. Okay, is equal to 1 plus G squared times ZT minus 2. So that thing is just steadily growing, and that's the driving force of the entire economy. Y will grow at the same rate. So the production function is secularly increasing at rate G every period. Y is increasing at rate G. C is increasing at rate G, and K is increasing at rate G. And if that's the case, then Z and Y and C and K actually have ratios that are stable. So C over K is a constant. Okay, the numerator and denominator are growing at the same rate, then the ratio is constant. We call that a grand ratio. Okay? The same thing is true of the wage in this model. This model is cooked that in the steady state, the agents obeying their first order conditions, no shocks, means that the wage is growing at the same rate as consumption is growing. So that actually looks like the German economy. If you just take the German economy over the past 50 years and you just compute those grand ratios, you'd be surprised how stable they are. So this drove Prescott to, he pushed the envelope and said, look, they're constant. My laboratory, they're constant. Okay, so he may have gone a little too far because we think maybe with algorithms and digitalization and all that kind of stuff may actually affect some of these production function parameters. So, but if you're willing to dispense with that in the first instance and just think about how this model behaves, it's quite beautiful. Okay, it's like a laboratory. Everything is just hunky-dory. You know, and then you've got these things that are constant. U is constant from period to period. The rental price of capital is constant. And the labor supply by the representative households in this model is also constant as a fraction of the day. Okay, so you may say that sounds crazy. But if you look at Germany and the United States in the past 50 years, the fraction of total available household time, including the women who weren't working, are working, the men that are dropping out of the labor force, that ratio is remarkably constant. It's about 0.3, between 0.25 and 0.3. You can go, and again, it depends on whether you include sleeping time, right? But it's remarkable. The United States is a little bit more. You might think that's because of tastes. So Prescott is pushing, Gillen and Prescott pushed the envelope on this. They're saying, okay, we're going to assume that these numbers are constant. U is constant, L as a fraction of the day, or the fraction of the period that's worked, in which working takes place. I think he included sleep, so his number was like 0.2. If you read his paper that I posted, I think he uses 0.2. Because it depends on whether you think sleep is part of your day or not. Okay. Okay, we call this a balanced growth path. So this is going to discipline the entire exercise. Because if I take those facts, if I take those steady state conditions and plug them into the model, then the first order conditions become very simple. They become incredibly reduced. And around that, we will approximate the model. Okay, so again, Y over K is going to be constant. C over K is the ratio of consumption to the capital stock. You can compute that for Germany. It's also constant in this model. And the wage share, which is the wage times employment divided by GDP, is also constant. If you go and look at the German wage share, you know, if you have to kind of cross your eyes, but you get the impression that the German wage share in the 1950s was low, like it is now, but in the 70s and 80s it rose, and then it went down again. But we're talking about maybe 5% of GDP, maybe depending on how you measure it. But again, we have to measure Social Security contributions because it's everything that goes to labor that the firms have to pay for. Okay, so this wage share is a bone of contention. But the model says it's constant. It's a Cobb-Douglas production function, competitive agents, competitive firms. And then basically we can plug in these conditions and get the three equations you see in front of you. So there's the Euler equation, or the Euler equation. You can see that C in the next period, when there are no more shocks, is equal to its deterministic equivalent. So it's 1 plus G times C. Okay, so you can just cancel the C, and you see that the equation to the right basically expresses this discount factor in the growth rate as a function of the capital output ratio. So the model disciplines, and if we take the model really seriously, the model has to give us an answer for y over k. Otherwise, it's just garbage. So the model, if you take, and this is Prescott, take the model seriously, you give me a number for g and beta, then 1 minus delta plus alpha times y over k has to be given by the left-hand side. Otherwise, the model is baloney. Okay? This gives you some freedom. We can basically look up, maybe we can look up delta in some accountant's book or some management textbook, and maybe alpha, we say it's the wage share. So in some sense, the model forces us to confront the data. If we don't have that, we don't have a steady state. Okay, so the model's garbage. The second condition is the intratemporal optimization margin for the household. You can see that puts a constraint on eta. Eta is the inverse of the Frisch elasticity of labor supply. Okay, remember that? So basically, we know that y over L is growing. We know that C is growing. They're growing at the same rate. So this puts a condition on L. And if we know what L is from the data, from household data, I told you Prescott thought it was 20% of your waking time is spent working, then that requires us to take a stand on eta. That's called calibration. So the data force us to take a stand on what eta is. Eta can't be just something I cooked up. Otherwise, it's not consistent with the data. Okay? This is why I get goosebumps when I think about this, because economists, we can do whatever we want. No one cares. We can be in the Sachverständigenrat. No one cares, right? What matters is who's running Volkswagen. But ultimately, if we want to be taken seriously, we have to have models that make sense. So someone's going to confront you with this someday and say, what about eta? Where does that come from? Did you estimate it using microdata? Or did you have some discipline from the data at all? Okay, and the last equation is simply an expression of a relationship from the resource constraint. And it's also very interesting. It says that you choose G, you choose delta, and I'm afraid you have to choose y divided by k minus c divided by k. It's a fact. It's a steady state condition. Okay? Now once we've done that, we can start log linearizing. Okay, this requires, again, using the Taylor approximation of first order of the logarithm of these variables. So again, I'm going to flash back. I'm going to take this system of 4 equations, and we're going to approximate it as a linear approximation around that steady state. Okay? Sounds like rocket science. It's not. It's not hard. Okay? It can be hard. I mean, you can spend a lot of time at your desk in the middle of the night trying to do this. Fortunately, or maybe unfortunately, we have computer programs that do it for you. So if you move to the next level, you can ask MATLAB Dynar to do this for you. But if you do that, you're kind of cheating. I mean, you're kind of you're trusting the machine. Maybe you want to do it yourself just to make sure you get it. Okay. So I'm going to give you an example of log linearization. We're going to take this resource constraint that I told you was ugly, and I'm going to try to massage it into a log linearized form. Okay. So remember, we had constancy of the grand ratios k over y, c over y along the path. The economy is growing at rate g, so those guys have to be constant. So the trend, you can write down the trend as being some sort of initial condition blown up by this growth rate every period, and k, et cetera. So we can take the Euler equation at the top of the slide and approximate it, okay? Or, if you like, take it literally. This is if you like, an approximation. If you think of this as being the percentage change or percentage deviation of k from its steady state path value, then that is exactly equal to this or approximately equal to that. Okay? So you can literally, all I've done here is I've taken this equation, I've rewritten it using Euler's constant raised to the logarithm of the variable in question. That's not rocket science, that's just mathematical identity. Okay? But the next step would be to substitute the hat values of k, t plus 1, the hat value of kt, and yt and ct, those are the percentage deviations. So that's where the approximation comes in. Okay? We're going to write the whole model in terms of the hat values. So the rest of the hour today, and possibly the next time, we're going to talk about the hat. This hat notation is the log linearized values of the variables of interest. Okay? So when I say x hat, I mean the percentage change or deviation from its trend. Okay? And again, you can approximate that with this expression, or you can think of it as the log of the ratio of the actual variable to its steady state value. This is something we did in the very first lecture, and it's coming back to haunt us, okay? So for small values of change, this is a very good approximation. And it's funny, the models that we play with, even in complicated models, the log linear approximation is pretty good. You can take it to a second order, but you don't get a whole lot of gain from that. Okay, that's fascinating. It's a very robust way of playing with models. That's why we're teaching it, and you'll learn this if you want to go further. If you love agents reacting to risk, for example, you think that the second order matters, then you have to do a bit more fancy approximation. Okay, so the hat notation allows us to write the expression like this, and then we can basically approximate it in the form like that. And all we've done is basically use the fact that what falls out when you do the log linear approximation is the grand ratio or the values of these variables that are trending along the path. So all I did is substitute basically for the values of k, t, yt, and ct, and I'm able to I'm able to cancel that steady state growth. In fact, I can divide both sides by k and get this final version of the log linearization of the resource constraint. So you can see that I've got k hat, t plus 1, and I've got this 1 plus g, that's a constant. And then I've got, it's a function of 1 minus delta, that's also a constant, times k hat t, so that's the previous deviation of capital from its steady state, plus a ratio times the deviation of output from its steady state, minus a ratio times the deviation of consumption from its steady state. So it has the same kind of taste of a resource budget constraint equation, but it's normalizing, it's kind of adjusting for the fact that you need to, if you're doing percentage changes, you need to account for the size of the relative variables. Okay, so this is our first log linearization. This is a really important step for you. This is one of the equations we're going to be massaging later, okay? Now we have to go back and look at the other equations and do those as well. And I'm not going to do this now because I want to get to the end of the lecture, but each one of these equations that I have here can be log linearized, and that's what they look like. Okay, and I'll go through them very briefly. The last one, of course, is the most fascinating one. If you log linearize the evolution of technology, that horrible looking thing becomes very simple. It just says that the log deviation or the percentage deviation of zt from its steady state in period t is simply a linear function of its lag deviation plus a shock. So that's the simplest, that's an AR process of order 1. So technology in this model is going to evolve as an AR1. So it gets shocked as long as rho is positive and pretty big. That means that future values of z are going to have some correlation with the past. And that's our driving variable. Okay? Now the other equations already did this one. We already normalized the resource constraint. And I substituted for the third equation. I already basically I substituted for these constants, and I've sort of solved it to get kt plus 1 on the left-hand side. That's all something you can do in the section. The first equation is the one that I told you from the beginning. You just take the log of that. You already have a log linear relationship. That was the intratemporal optimality condition. So that's also easy. It also has no expectations because labor supply today is based on the wage observable today and consumption observable and determined today. Okay? The only one that's really kind of tricky is this second one. So this is when you have to really write down something. This is the approximation, the log linear approximation of this intratemporal condition, the evolution of the marginal utility of consumption over time. Okay? So when you do that, the approximation says we log linearize the relationship, and then we take expectations. It's not the case that the expectations of a product or a log is equal to the log of the expectation. That's wrong. Okay? So the idea is you take a linearized approximation to this relationship, and then you pass the expectations operator through, and you get the following relationship. And all this obtains because what matters is the expected rate of return on capital, and that depends on my choice of labor tomorrow and my choice, my technology that I'm facing tomorrow, and my capital that I've chosen to have tomorrow. So this is the intertemporal macroeconomics coming full force. This Euler equation is the macroeconomic dynamic driving force of the model. So if you look carefully at this, we have 4 equations still, given my state variables of the past and given my expectations of the future. So we actually have a linear system now, a linear system in 4 equations, and 4 unknowns. Except now we have these hats, these deviations from the steady state path. So this is, if you understand this, we're on our way. Because all we have to do now is just solve that funky looking difference equation system. Now it's a 4 equation system with 4. It's not a simple one like we did before. It's a little bit harder. I want to take an excursion and talk about calibration. I already mentioned it, right? I already mentioned we need the data to sort of force us to take a stand on certain parameters, otherwise the model is no good. This is not an exercise in mathematical, self-satisfaction, if you like. Could have said something worse. But I'm on tape, so I have to be careful. So the question is, where does this stuff come from? Can I just throw in an eta, or can I just toss in an alpha or a beta the way I feel? I'm in a good mood today. I think people have a high beta. No, you can't do that. So let's be really clear on this. The linear coefficients in the last slide come from the model. Okay? So they're functions of the deep parameters. So this is something we talk about in macro a lot. The model yields sharp implications, and if the model's implications are too sharp, the model is no good. Okay, so it's a very sparse model. It has a few parameters: alpha, beta, eta, g, and there are a couple others. Okay, other things we have to, everything else. So the data can actually give us some guidance on what values of this setup are admissible. Okay, so they cannot be reality free. We can't just choose alpha out of the hat or just sort of, I feel like beta should be 0.9. It has to have something to do with the data. So Prescott was really dogmatic about this. He said it has to match the data. If we're going to use this model as a laboratory, we better be sure that the implications of that laboratory match the stuff that our Statistisches Bundesamt is telling us. Okay? So the capital share should look like alpha. Okay? G should look like the average growth rate in your economy. And C over Y and K over Y, you can calculate that every quarter using the German statistical, the Volkswirtschaftliche Gesamtrechnung, the statistical accounts of the German economy. So you should be able to do this. The data discipline the model. And if you can't do that, you should probably toss the model. Now, I'm going to post a very interesting article by Prescott, a fascinating article. It's called, "Why Do Americans Work So Much?" And, compared to Europeans, it's a fact that Americans work a lot. We don't take much vacation, okay? I mean, on paper you get two weeks vacation, but in fact, a lot of people don't even take that. In Europe, 5 weeks, 6 weeks. In France, 6 weeks. It's a great country. And productivity per hour is very similar in both countries. Germany, US, and France. Up until the 1990s, they were almost identical, actually. And then there's been some, maybe because of globalization, maybe because of automation. But in any case, Americans work a lot more than French people. And the question is why? So Prescott actually asks this model to tell him. Okay, and this paper is very controversial because he says it has to do with taxes. The model implies that. If you put taxes in the model, it implies that people who have lots of taxes are going to work a lot less. Okay? So I urge you, if you think this is a cool methodology, take a look at that article. It's easy. You can read it in the bathtub. It's very easy. Okay? And it's actually quite interesting. He pushes the envelope. He's always pushing it. you know, and you can say, well, that's going too far, but take a look at it. You might learn something. I certainly did. Okay, so this implies a general approach to doing this DSGE business. We call this dynamic stochastic general equilibrium. That's what DSGE stands for. Usually it's applied to the new Keynesian models, but it's also a characterization of what we just did. Okay, so I'm going to write this down for you. State the model clearly. What are the preferences of your agents? Are they maximizing? What's the technology they're using? What are the technologies that the firms are using? What are the constraints? You can't do anything you want. You have constraints. What's the market form? We have competition. Do we have monopsony? Do we have monopoly? What is the equilibrium? Okay, that's the first thing you do. Then you write down the first order necessary conditions of these agents. Okay, that's already quite a bit of ink you're spending or wasting on that, okay? And then you got to characterize the equilibrium using these first order conditions plus resources constraints or other identities or a transversality condition as discussed already. Identify the steady state, log linearize the model around that steady state, and then you solve the model, which we're about to do. Okay, so I'm certainly not done yet, okay? And you can use calibration to get the parameters, or you can actually use econometrics. Now, some people are anti-econometrics. Some professors, some researchers don't like econometrics. Some economists love econometrics. So you have to take a stand on that. Do you want to use econometrics to estimate the parameters? Do you think that they're estimable? There's a whole set of papers on this. Okay, but you can do both. You can actually do both. And then finally, what we're about to do is you actually shock the model and see how it responds. How does it behave away from the steady state and how it comes back? Just one shock. And then, of course, the real world is every day, shock, shock, shock. Okay? That's the way it works. That's what we're going to do. So let's study the approximation. You might notice we had employment in that system of 4 equations. Well, employment is a function of contemporaneous variables. It's a function of y today, k today, and c today. So we can actually substitute it away. We can get rid of it. So we can make it a 3-variable system and 3 unknowns. Okay, that's nice. And then we can write it down in the way that we used to from the last lectures. We looked at difference equations, and then we can solve it. I'm going to show you how to do that now. Okay, there are 2 ways to do this. One is the so-called eigenvalue decomposition method, which is beautiful, it's elegant, it's fancy, it's lovely. And my thesis advisor actually invented it. So I really like this approach. Okay, so it's going to be called looking at the Blanchard-Kahn condition. Okay, so I like that. But you can also use the method of undetermined coefficients, which is the easy shortcut way. Okay, so those are the 2 ways. And it turns out that even if you do fancy solution methods, they usually use the method of undetermined coefficients in some way. Okay, so let's approximate the model. And what does it mean to solve? So I'm going to take you through both of these right now. Okay, so the first one is called the eigenvalue eigenvector decomposition, or the matrix eigenvalue decomposition. So again, I'm going to use the matrix notation to help us write this in a quick and dirty way. Okay, it's going to look like this. It's going to express the endogenous variables tomorrow as a function of the endogenous variables today. Now, where are the shocks? Well, we're looking at the deterministic equivalent. We're looking at basically where the model would be going if there were no more shocks. Even if we're away from the steady state, how do we approach it? Okay, so again, this looks very much like the ASAD model we manipulated a few weeks ago. Okay, so you have expectations of the future, and you have the current values of the variables. 2 of those are state variables in the strict sense, and the other one is the control variable that the consumer is choosing in this approximated world. So this is a 3x3 matrix. A is a 3x3 matrix, and basically if you want to put the shocks in, it looks like that. So once we start shocking the model, we can't have expectations. We're going to have the actual realizations of these deviations. So you'll basically have the same bit here. It's a linear model with this shock. And the shock affects z directly. We know that from the equation. It also affects ct plus 1 directly, but through the coefficient a, which is the way the consumer responds to the fact that his production function that his companies are working with is more productive. Okay, we'll get to that in a second. But the important thing is we want to look at the properties of A. We care about the stability condition of A. Remember, A is simply taking all those constants from the log linearized thing and putting them in a box, in a 3x3 box. Okay, so we're going to study the properties of that box, that matrix, to see if it satisfies the conditions that we remember vaguely for stability. And if you still remember that just a few weeks ago, for absolute stability, we required A to have eigenvalues that are all inside the unit circle, right? Otherwise, that thing's going to blow up. And we don't want the model to blow up. We want it to actually come back to Earth. Remember? Okay, so we're going to take you through this now. Watch this. I'm going to require you to remember what an eigenvector is and what an eigenvalue is. If you've forgotten that, then you're going to have to go back and crack open one of your books on algebra, matrix algebra. It's really important. So bear with me, and Andreas will give it to you again in the coming sections. Okay, so A can be decomposed. Under the conditions that we've got in this model, there's going to be a unique representation of A as the product of three matrices. You can have omega, which is the matrix of the eigenvectors of A, and omega inverse, which is the inverse of that matrix. And in between is a diagonal matrix that consists of the eigenvalues of matrix A. That's called the eigenvector, eigenvalue, eigenvector decomposition. Okay? So the eigenvalues are quite important because they're going to appear in lambda. This cap lambda, what did I call it before? Cap lambda is the matrix, it's diagonal matrix, 0 is off the diagonal, and on the diagonal I have these eigenvalues. And I'm going to order those eigenvalues in decreasing size. Sorry, in increasing size. They're going to increase as you move down the diagonal. It's kind of an important thing later. Okay? So now we're going to take that difference equation we had before, and I'm going to pre-multiply it by omega inverse. So I'm going to, and if you remember, one of the things I love about matrix algebra, if you think about multiplying a vector by a matrix, it's like turning the vector. It's like twisting it or turning it. Okay? It's like putting it in a different direction. It's just a linear transform of a vector. So if you take a vector and you hit it with A, it's going to look like this afterwards. Okay? So the question is, what's so special about the eigenvector? If you hit the eigenvector with A, it basically just stretches A or compresses it. It doesn't change its angle. Okay, so if you pre-multiply that system that we had before by omega inverse, you're going to end up getting something that looks like this. Okay, omega inverse will wipe out A and turn it into this diagonal matrix. And the diagonal matrix means that only the own variables matter. So this transformation of K hat, Z hat, and C hat is a rotated system that each one of those variables that only depends on its own value. Remember, these are all linear combinations of K hat T plus 1, Z hat T plus 1, C hat T plus 1, and they're only a function of their own past. And that means that the properties of this system are going to depend on the values of those eigenvalues that we have in the lambda matrix. So if you remember before, we said for absolute stability, all the lambdas have to be smaller than 1 in absolute value or in modulus. That means that if you keep hitting this thing, the thing's going to actually damp down. Okay, and you can see it's black and white right here. If the elements of lambda are all less than 1 in absolute value, then if I keep hitting this thing, it's going to get smaller and smaller. It's going to go to 0 eventually, because all these things are normalized around the steady state, so they have expected values in the long run. And the unconditional expectation is 0. So if you let that thing go off, it's going to go to 0. Okay? So we're going to call, this is just a trick. Okay? So I want you to remember the hats. The tilde is kind of just a trick. So the tilde is a rotated version of the hats. And it turns out that this rotation has this magical property that these tilde variables only depend on their own lags. And again, if you understand what a linear transformation is, K tilde is a linear combination of K hat, Z hat, and C hat. So it's just saying that rotation has a temporal dependence that is defined by its eigenvalue that's in that location of the matrix, lambda. Okay? So that, this is just a linear combination. The linear combination is based on the inverse of the eigenvector matrix. So that's just a linear combination. Think of it as a rotation. I hit the vector, it goes over here. But we rotate it such that what's left actually only has a temporal dependence on its own past values. Now, why did I do that? Well, I need to use that global stability problem and think hard about this, because it turns out that in this model, all eigenvalues do not lie within the unit circle. Okay, so this is the most important thing you're going to learn today, is that the global stability is violated in our wonderful RBC model. It's violated because one of the roots is actually outside the unit circle. So back in the 1970s, this was considered a real crisis. People thought about this real hard, and Blanchard and Kahn wrote down this paper, very short paper in Econometrica, where they actually prove that under certain conditions, the thing is still stable, it's saddle stable. So there'll be exactly one value of the control variable C that actually hits the number, gets us back on the convergence path, which takes us to the steady state. Okay, so it turns out that two eigenvalues of A are inside, and one is outside. And again, the crisis was, things are going to explode. It's true that if you take any value of C and plug it in there, it will explode. So that's a problem. But there's exactly one value of C for which it doesn't explode. And I ask you to think back to Ramsey. Remember Ramsey? So now you're going to have an epiphany moment. You're going to think about Ramsey and the social planner choosing consumption to get back on the stable manifold. That's exactly the same idea. Okay, except it's a discrete time model. It's the same idea. Okay, and the eigenvalue conditions are different because it's a continuous time model. In Ramsey, this is a discrete time. So the continuous time model, we don't spend much time. You just take a growth theory course. But if you take the discrete macro approach, the modern macroeconomics, we look at this Blanchard condition, which says that basically you need to have sufficient number of roots inside the unit circle for this model to have saddle stability. Okay, and it turns out that the Blanchard condition says that you're allowed to have as many roots outside the circle as you have jumping variables or control variables. In this model, we have one control variable and we have one root that's outside the unit circle. So we're in business. Okay, so that Blanchard-Kahn condition is a cornerstone. If you go on to take Weinke's macro course, it's part of the story. It's going to be part of the new Keynesian models we look. Anytime you have agents that are looking forward, you have a problem with global stability. And basically, if the agents are doing the right thing, there's going to be one value, possibly more, but there's usually going to be one value that will get you back on track. And we're dealing with a model where there's exactly one value of CT that's going to get us back on track to go to the steady state. Okay? So I'm going to try to prove that to you intuitively. We rotated these variables, okay? And we realized that when in the rotated form, any value of, just take C tilde. C tilde is a linear combination of previous variables, but we know that C tilde only depends on CT in its past. Okay, so C tilde t plus 1 depends on CT or some power of lambda times C0, the initial condition for C. Okay, so we know, on the other hand, that lambda 3 is greater than 0 in absolute value. So under any old random C, you take a random C0, I'm going to have an explosion. I can make CT plus 1 arbitrarily large just by taking T large enough. Okay? So keeping the model in a non-explosive mode requires that C tilde has to be 0 for all T. Okay? So the agent has to kind of behave in such a way that this linear combination, which is fixed, of the original variables has to always equal to 0. So that means that CT there's only one value of CT that works. Okay, and that's why it's called a jumping variable. CT will jump, CT hat will jump to the value that satisfies this equation in all periods. So CT lies in the stable subspace, if you like, of KT and ZT. So we call C a jumping variable, and in order that C tilde is equal to 0 in all T, C hat has to take a certain linear combination of KT hat and ZT hat. Okay, so we can actually find that because we know that these transforms are basically the inverse eigenvalue matrix, eigenvector matrix pre-multiplying that vector. So I can reverse engineer. If I know that C tilde has to be 0, then I can reverse engineer by taking this expansion taking the last row of this inverse eigenvector matrix, multiplying it through the pieces, I get this linear equation. I can literally express CT as a linear combination of KT and ZT. Okay? Wow. Okay, so we've pinned down the stable manifold, the saddle stable solution. CT has to obey this equation, otherwise the model explodes. So the RBC model has an inherent instability. I mean, it's kind of but it turns out there's exactly one value of CT that does the trick. So agents are smart enough to understand that if they consume too much, the model will basically run off track. If they save too much, the model will run off track. But if they choose this value, it's going to work. So that's kind of what the solution in general of log linearized systems of models with rational expectations impose on us. So this is a really important statement I just made. I'm going to repeat it now. State variables cannot jump. That's the way it works. The only thing that's going to save us is the behavior of consumption. So the co-state variable is consumption, just like in the Ramsey model, just like in growth theory. Same idea. It's beautiful. Okay? So saddle stability in this model is the condition that the number of stable roots is equal to the number of state variables. We had two state variables in this RBC model, this reduced RBC model, capital stock and technology. They depend on the past. They can't be changed except for they can't be changed by choice. Okay? CT is a linear combination of those, and the Blanchard condition says that basically you got to have two roots inside the unit circle for A. And that's something we can actually check. And you can imagine that not all parameter values will satisfy that condition. That's another discipline of the data. If we don't observe an explosion, in some sense the model has to satisfy that condition as well. This is called the Blanchard-Kahn condition. The reference is Blanchard-Kahn, 1980, Econometrica. Okay, it's still used today. A lot of advanced versions of this are being used. Klein has a paper where he talks about a QZ condition, which takes account of other having extra variables that are linear combinations of other contemporaneous variables. There are other things you can, but the fundamental point is here. The second solution method is a piece of cake. It's easy. It's called the method of undetermined coefficients. Okay, so we learned already that CT hat is a function of KT hat and ZT hat. We kind of know that. We learned that in the first approach. Okay? So in a sense, the consumption policy rule depends on the current state in a linear way. So if we know that, we can just plug it in and solve it. So again, this is really easy. If you're willing to just do it, and you don't even have to use matrices. You can just do it like and if you read Campbell, 1994, he actually does it without recourse to any matrices at all. You just do substitution. Okay, so we know that households have a rule that looks like this. It's a linear combination of KT and ZT. So the optimal choice of the household, because of our model, says that it's going to be a linear combination of the capital's deviation from steady state and the technology deviation from steady state. And those etas are constants. They're elasticities because we're talking about log relationships. So think of eta CK as the elasticity of consumption with respect to the capital stock. Okay, it's just the way, that's what elasticity does, okay? And then we just substitute that back into the value of C and then solve for those etas, eta CK and eta CZ. And then we're done. So this is really easy, okay? You can do that on an exam, basically. You just, if you're fired up, you can do it, okay? So the solution to that is exactly the same as the one with this complicated eigenvector, eigenvalue decomposition. Okay, so it's nice. We get a confirmation of what we did before, and depending on your mood, you can try one or the other. It's nice to look at A and its eigenvalues because it tells you right away whether you've got the model stable or not, or saddle stable. Okay. If you take more advanced courses, you might learn that this A matrix under some models actually has more stable roots than you need. So it actually has you have like a super stability or a indeterminacy, they call it. Okay, but that's a. Okay, so once we've done this, we can actually ask the question, what happens if I shock the model, and I'm going to shock it with a positive productivity shock? How does the model respond? Well, what we've done now effectively tells us the answer. We know that consumption is a function of K and Z, and K and Z are given. And when the shock occurs, we have a new value of Z, and the households are going to save more. So it's like you put the machine into motion, just like we did before, and we can actually trace out this response. So this is, even though agents have rational expectations, they're actually forming expectations based on the past, which are rational, and it gives us a stable behavior. So this is taken from a paper by Harald Uhlig, okay? So he's actually shocking the model I just gave you with a value of eta, which is very high. Okay, so this means that households really react very strongly to changes in the wage. Now, a lot of people will contest that, and again, that's something we'll talk about, the weaknesses of the model in a second. Okay, but look what happens. Output rises. That's because of the shock, but also because people are working harder. So a positive shock in quarter 0 leads to more output directly because of Z going up. People work harder because they're more productive, the wage is higher, and they're elastically supplying their labor. In subsequent periods, you're going to have more capital because agents don't consume it all. They can either consume or invest, and the agents want a smooth consumption, like in Ramsey, and also like in these models. They're going to take a little bit of that capital, take a little bit of that extra output and put it into the capital stock. So look what happens to the capital stock. It's growing. Why is it growing? Because agents know that the productivity shock that occurred in period 0 is going to persist for a while, so it's good to have some capital around. Okay, so if you look at that, that looks like a classic boom. It looks like the 1990s. If you take this model, if you really want to take this model seriously, like some of my colleagues do, this kind of, the high point of this was the 90s. We had the tech shock, we had, internet, Al Gore invented the internet. You're supposed to laugh. Crazy investment in the United States, but also in other countries. And then we had big, the Clinton years were pretty good. I think a lot of people would say it's because of the internet. It wasn't because of Clinton. This is kind of what we'd like to see. It's a real technology shock, okay? You can see that consumption is smooth relative to investment. That's exactly what we see in the data. God, it's great. And labor, eventually people work hard, but then they start getting a little bit lazy because they got all this capital and they feel wealthy, okay? And what the wealth effect says, well, at some point we're going to kind of hold back a little bit. And of course, over time, the incentive to work hard goes down because wages start to fall, because the technology shock starts to die out, okay? So you might say, wow, we're done. Let's go home. Okay, but it turns out there are a lot of weaknesses of this model. There are a lot of strengths. The strength is obvious. C and I are pro-cyclical. You get the variability right. Investment is very variable in this model, and if you shock it a lot of times, you get the same thing. Interest rates are pro-cyclical, and it's easy to understand this model. Okay, we can all understand it. We may think it's crazy, but we understand it. It's a laboratory, okay? It is in fact the case that the variability of output is not so tightly related to the variability of monetary policy. If you do a serious exercise trying to attribute how much variability of the US business cycle since 1970 is because of monetary policy, you don't get that much. You might get 25% using serious econometrics, okay? Again, the variability looks like this in the US data. It looks like this in the OECD data. So the RBC model hits that pretty well. It turns out that consumption of government doesn't really have that much correlation. When I saw this, I was shocked. Okay, there's no government in our model, but you can put it in. It doesn't help much. Okay? Labor productivity is pro-cyclical, and interest rates are pro-cyclical. And it turns out if you look at government spending actually has a positive effect in this model. So people like Baxter knows or put government spending in this RBC model and to ask what happens. The RBC model says that the government, when the government comes in, it's like taking stuff and throwing it in the ocean. Okay, think about it. Military spending is kind of like, it's a waste, right? You might think, oh, it helps us, but does it really help you in your consumption? If you don't use it, it's a waste. So it turns out that in that model, when the government increases government spending in a sudden way, it actually, in a temporary way, it causes people to work harder because they feel like they're getting screwed. Because the government's taking stuff, literally, and just dumping it in the ocean. That's the way this model works. So you might say that's a weakness. That's not the way I think of government spending. I think government spending, building the Autobahn, adding some what's called Hochgeschwindigkeitszüge and all that kind of stuff. Infrastructure, good for Germany, blah, blah. Rebuild Kennedy Airport. I don't know if you've ever been to Kennedy Airport. That sort of stuff. Well, we have to extend the model. We need to have a productive effect of government spending to make that work. The government spending surge would have to help productivity. And that's very, very, very hotly contested. A lot of people don't believe the government on net does a lot with its spending. So it's kind of an ideological question. Let's just stick to the model. The model has weaknesses, okay? The weaknesses of the model, it has a constant wage share, which we saw in the data is not true. So the model cannot hit that. That's because of the Cobb-Douglas assumption. And possibly because wages are determined competitively in that model. And if wages were determined by bargaining or maybe monopsonistic firms, maybe you'd have more play in the wage share. The model is also bad because it doesn't deliver a lot of persistence. Okay, it looks like persistence in that Euler picture. You can go back and look at it, but it's not enough. And all the persistence comes from the technology shock. The capital stock is not sufficient to get this to work. So you got the negative smiley there. Okay? And if you add government spending, the model predicts that government spending works because it actually impoverishes people, not because it stimulates the economy. So to get the idea of stimulating the economy, you need something like a Keynesian mechanism. So the rest of my course is going to talk about the Keynesian model, which says that that's not the way the world works. The world works differently because prices don't react completely in the current period. Therefore, money does matter, monetary policy matters, and the rest. Okay, so you can see this is kind of. I want to show this to you so you can see the pictures. The picture of the Burns-Mitchell shows that real wages are actually not moving very much. Okay, over the cycle. This is the Burns-Mitchell thing. So, I mean, either eta is really, really high. People have an incredible elasticity. This little tiny increase in the wage is enough to get people to really work hard, or the model is absolutely mad. It's just crazy. Okay, you take your pick. Also, this wage share bothers me a little bit. So in a recession, the wage share actually rises because productivity falls faster than the wage. Remember, the wage share is the ratio of wage to productivity. Okay? Write that down. Wage divided by productivity. Okay? So that doesn't work. Okay? So the model has all these weaknesses, and a lot of people get really upset about the no money, but also unemployment. Where's unemployment in this model? Do you know what unemployment is? Did you see it? Unemployment is voluntary in this model. It's the household withholding its labor from the market. Okay? Now, think about that. That says a lot about unemployed people. The unconditional statement in that model is pretty negative. And I know a lot of people who've been unemployed, and they're not always very happy. Okay? And the model predicts that the representative household is kind of holding back because wages are too low and time to take a break, that sort of thing. But again, it's a model, and it got 2 guys a Nobel Prize, and also gave us a whole toolkit of things to work with. Most importantly, and that's tomorrow, is money. If you look at that picture, you see that the real money supply is extremely, extremely cyclical, and it's a leading indicator. Okay, so you can see that about 6 to 4 quarters before the peak of a cycle, the real money supply starts to peter out. Now we know from the banking literature, we know from banking, our knowledge of banking, crude as it is, money supply on the liability side is mapping into credit on the left-hand side. Okay, so money is credit. So one way of thinking about this is that extension of credit by banks slows down about a year to 6 quarters before the recession kicks in. Okay, so we're going to spend some time thinking about these challenges. Okay, how seriously should we take this model? Okay, what are the welfare implications? And I'm going to let you answer that on your own. Is unemployment really voluntary, or is part of it? Some people would say, I think unemployment is a mix. I think that some people are kind of postponing the inevitable job they have to take because they're not getting the job they want, or the jobs they have are not very attractive. And then, of course, we need to think about money. Okay, so next week and the weeks to follow, we're going to think about the Keynesian approach, the new Keynesian approach to this. Thanks for your attention, and I hope to see you next week. Bye.